Welcome to the afternoon session of the ISQGD Ergo Dictionary and Topological Dynamics session. Our first speaker is Svetlana Katok, and she will talk about rigidity and flexibility of entropies of boundary maps associated to mispronouncing, Fuchsian groups.
Thank you. Thank you very much. So this is a joint project with Adam Abrams and Ilya Ugarkovich. So let me start with the setup. Gamma will be co-compact torsion-free Fuchsian group, which is also called surface group. It's a subgroup of PSU11 acting properly discontinuously by orientation-preserving isometries on the unit disk D. So those are Möbius transformations. Euclidean boundary is a circle at infinity, and a function on the circle is boundary map if it acts piecewisely by generators of gamma. In 1979, Bow and Sirius constructed a boundary map for any such group using fundamental 4G gon, and this map is orbit equivalent to gamma with Markov property on finite partition of the boundary. In 1991, Adler and Flateau studied Bow and Sirius map for surface groups using different fundamental polygon. They were using 8G minus 4 gon, and we found this is very inciting. In 2017 and 19, I worked on this with my co-authors, Ilya Ugarkovich and Adam Abrams, and we studied families of boundary maps for surface groups related to this AG minus 4 gon, and we proved that their two-dimensional natural extensions have global attractors with finite rectangular structure. So now I want to talk a little bit about this 4G minus AG minus 4 gonal fundamental domain, because it's not so common as regular in topology 4G gons. Okay, so any compact orientable hyperbolic surface of genus G greater than or equal to 2 admits such a fundamental domain obtained by cutting the surface with 2G closed geodesics that intersect in pairs. So this left picture shows that G of them are around holes and G around the wastes. You can make this picture for any surface of any genus. This is for genus 2. And when you cut the surface, then you get exactly 8G minus 4 gon. So we were trying to find out, apparently this goes back to Dane, Fenchel, Nielsen, and Kobe, but Adler and Flateau actually proved rigorously the existence. Okay, so now identification of sites is by involution, which is given by this formula. And in the right picture, this line show the identification. So this site is identified with this site with this site, this site with this site, and so on. They obtained this way AG minus 4 gon does not have to be regular, but it satisfies the following two properties. First, the identified sites K and sigma of K have the equal lengths, obviously because we cut it, and the angles at glued vertices add up to 2 pi. So we call such a polygon a marked canonical polygon. Now, if F is regular, it is centered at 0 and all angles are equal to pi over 2. Now, if you have any AG minus foregone with these two properties, then when you glue them up, then you get exactly genus G surface. So the maps which identify the size, so TK, it maps side K to side sigma of K. This maps generate Fuchsian group of the first kind with signature with genus G and no elliptic points and no parabolic vertices. So exactly Fuchsian group. Okay, so now let's recall that for genus G surface, there is a whole Teichmüller space of Fuchsian groups, which have the same signature up to conjugation by orientation preserving isometry. So this Teichmüller space has dimensions 8G minus 6G minus 6, sorry. So now, suppose you have two surfaces of the same genus, and one is obtained, for one, the fundamental polygon is regular, for the other is irregular, like in this picture. By Fenchel-Nielsen theorem, there exists an orientation-preserving homeomorphism of the disk, which is extended to the boundary, which conjugate the groups. So now, since this homeomorphic orientation preserving, it preserves the order of points on the boundary. So I use, I denote the endpoints of geodesics forming the fundamental domain by P1, then Q1, P2, Q2, etc. So the order of this under H is preserved. And so we want to construct the fundamental domain for group gamma. For this, we connect H of Pk and H of Qk plus 1 by geodesics. And you see, since the order of the points is preserved, then it turned out to be AG minus foregone again. But of course, we need to prove that it satisfies this properties 1 and 2, that this sides, identified sides have the same length, and the angles add up to pi, which is true. And so we get a marked canonical fundamental polygon for gamma with the same combinatorial structure as F regular. So by that, I simply mean the identification is of the same. So this construction gives a less common representation of the Teichmüller space T of G for G greater than or equal to 2. It's the space of marked canonical AG minus foregons on the unit disk up to an isometry. Okay, so now I will talk about the family of boundary maps. So for any marked canonical fundamental polygon, AG minus foregone, if we only look at P's, so I call it partition P bar, and if we only look at Q's, so it will be Q bar. So Pk and Qk plus 1 are the endpoints of the corresponding geodesics which contain size K. Okay, so now I'm looking at multi-parameter. I take AK between Pk and Qk. So it's the full interval where I'm allowed to take my AK, and so for each K between 1 and 8G minus 4, this is a multi-parameter. A. And so now, instead of just looking at one boundary map, I'm looking at the full family of boundary maps. And the definition is the following. So it acts by transformation T sub k if X belongs to interval between AK and AK plus 1. Okay, so here the Vaughan series and Adler and Plato. Okay, so now what kind of deformations we are going to look at? Well, this picture shows this is a regional P transformation. So one thing is to look at the Teichmuller space. So under Teichmuller space, the polygon changes, okay, but it still stays as P. But the other transformation is you keep the polygon, but you change interval where each T sub k is used. So you change the multi-parameter between PK and QK. So I call this multi-parameter external if AK, each AK is either PK or QK, so there are finitely many of them, of course. So in particular, P and Q are extremal. And if AK is between PK and QK, so in 2017, we proved that A satisfies so-called cycle property. So what I mean by that is that AK, so formally speaking, there is the transformation is defined uniquely at TK, but you also can look a little bit to the left of TK and a little bit of the right, okay? So then you either use TK or you use TK minus 1, okay? And then if you look at the orbit of TK AK and TK minus 1 AK, turned out that there exists some integers MK and NK such that these two orbits coincide from some point on. So we call it cycle property. If both MK and NK are equal to 1, then we say that this partition satisfies the short cycle property. So they coincide after one step. Okay, so these properties are preserved by Fenchel-Newton homeomorphism. So it makes sense to talk about multi-parameter satisfying these properties in the Teichmuller space. Now, each FA is piecewise monotone, piecewise continuous map because it's piecewise Möbius transformation. And well, it's Möbius transformation on the disk, but of course it's not Möbius transformation of the circle, but it's still monotone, piecewise continuous. If A is extremal or satisfies short cycle property, then FA admits a unique smooth invariant ergodic measure related to the Liouville measure for the geodesic flow. Okay, so now I can state two very, very different theorems, rigidity and flexibility theorem. The first is about topological entropy. So from now, S will be always the surface of genus G greater than or equal to 2, and F will be this canonical AG minus foregone in the Teichmuller space. So the first theorem says the following. If we take any multi-parameter with AK between PK and QK and look at this boundary map FA, so they all have the same topological entropy, which is given by this formula, which only depends on the genus. Now, I should notice that FA bar, they are not generally topologically conjugate. So it's not trivial what I'm saying. So because combinatorial structure of orbits associated with each partition point could be different. So this is rigidity of topological entropy theorem. Now, the measured theoretical entropy, on the other hand, is completely flexible. And this is in the spirit of flexibility program suggested by Anatol Katok, and we heard about this already in the previous session. So let A be either extremal or satisfy the short cycle property. So this is an open, well, of course, extremal, there are only finitely many of them. But short cycle property is an open condition. There is an interval inside Pk and Qk for each k, which satisfies the short cycle property. So then, first, there is a very nice formula for measured theoretic entropy. It's pi times area of the fundamental polygon divided by perimeter. Second, the maximum value of measured theoretic entropy is achieved on the surface with regular polygon. And the third is flexibility. So for each t from 0 to maximum, there exists an f in the Teichmüller space for which measure theoretic entropy is equal to t. Okay, so I'm very afraid that I will be out of time. Okay, so let me quickly indicate what kind of tools I'm using. Well, first of all, the topological entropy of one-dimensional maps. So Bowen definition, which was given for continuous map, it also can be applied for piecewise continuous, piecewise monotone interval maps, and also can be extended to circle maps. So Perry in 1966 proved that a continuous piecewise monotone topologically transitive interval Markov map with topological entropy H is conjugate to a map of constant slope e to the H. So Mizurevich-Schlenk, they also prove kind of the opposite, that if you have a map with constant slope, then topological entropy is conjugate to map with constant slope, topological entropy is equal to log lambda. And Alsed Mizurevich to 2015 proved this for piecewise continuous maps. Now, in the rigidity theorem, so there are the following steps. Okay, so we first consider two Markov cases. Essentially, we are looking at P and Q. Okay. So this works for any extremal, but for now we're only interested in P and Q. And so this is basically a brute force. These both maps are Markov, and so each has Markov matrix, and the number of A admissible words of length n grows as lambda to the n, where lambda can be computed directly. So from this, we know that topological entropy for Fp is equal to topological entropy of Fq. How about when we are in between? Now, when we are in between, we know by all these authors I mentioned before that this map Fa is conjugate to a map with constant slope. Okay, so the picture for Fp and the corresponding linear map is shown here. Okay. Now, the main theorem, the hardest result of this is that actually this conjugations Psi-P and Psi-Q coincide. Okay. So I don't obviously don't have time to talk about the proof, but it includes explicit formula for this conjugacies via second Perry measure, relation between Markov partitions and cylinder intervals, etc. So completion of the proof, this conjugacy, which is common for P and Q, actually works for all A between P and Q. Okay, and it is piecewise linear with the same slope, and therefore the entropy is the same for all these maps. So that's roughly how the proof goes, but this part is rather involved. Okay, so how about theorem 2 about flexibility of measure theoretical entropy? Well, I really don't have much time. I want to say that there are, well, of course, we are on the unit tangent bundle to the unit disk, and we have Liouville volume, which comes from hyperbolic area of the upper half plane. So the omega, but it also can be written in different coordinates. And these coordinates are UWS, where S is the arc length along geodesics from U to W. So there are 3 parameters. So this dm is d nu ds, where d nu is the smooth measure on the space of oriented geodesics, modeled as S cross S minus diagonal. And this is called geometric current. So we proved that two-dimensional map which is using so it's essentially a natural extension of FA, because FA is not invertible, but FA. So it preserves the smooth probability measure d nu divided by the integral of the nu over the attractor. So the main point here is that there is an attractor, global attractor omega A with finite rectangular structure. Okay, and so a geodesic flow can be expressed as a special flow over a cross section parameterized by this attractor. Okay, so the point, of course, geodesic flow can be represented as a cross section, as a special flow over cross section, many different ways. Okay, so this particular way is convenient because we know a lot about this omega A, and we can actually compute. We can compute the integral. Okay, so now the boundary map is a factor of FA. So if one can obtain the smooth invariant measure on S as a projection of smooth invariant measure on the cross section. So okay, so let me just I basically am out of time. Okay, so formula for entropy. So how this area, well, the formula which we obtained in 2019 is the following. It's some number which is pi times area of the fundamental domain, okay, divided by this integral over the attractor. So the area, this is essentially area of the attractor. Okay, so how the parameter, how this perimeter comes into the game. Okay, it turned out that this integral is equal to the perimeter. And the reason for that is that there is a bijection, there is a geometric map. Let me see. So there is another map, which is kind of related to this attractor, but it's defined not by the interval on the boundary, but by the side K, the geodesic exits. Okay, so these two pictures, this picture shows two maps. The rectangular map is the attractor, okay, and curvilinear map is this geometric map. And it turned out that there is a bijection, piecewise Möbius bijection, which maps bulges to corners. So the corners are red and bulges are blue here. Okay, well, that means that these two areas, these two domains have the same hyperbolic volume. Okay, so and then the last step is that there is a theorem by Bonnechen that integral over, if you look at all oriented geodesics which intersect at the geometric segment S, and this integral is the length of S. So from this, we have this perimeter thing, and I'm afraid that I'm really over time. Okay, so maximum of the entropy is not very difficult. So among all hyperbolic polygons with given area and number of sides, in the same number of sides, the regular polygon has the smallest perimeter. Okay, so this is a reference. And flexibility follows from Fenchel-Nielsen coordinates on the Teichmüller space. So one of the geodesics can be made arbitrarily long, and therefore the perimeter will be arbitrarily large, and so the metric entropy will go to zero. Okay, and then the continuity follows that. From continuity, we see that it can take all the values between 0 and maximum. I think I should stop here. Thank you.
Thank you for a very interesting talk. Hold on a minute, we'll do the stopping the recording.